Hello everyone. Thanks to everyone for watching this video. My name is Qi Dang. I'm an architect and engineer. Today's video is titled Fire Resistance, and it is going to provide you a broad overview of the tensile membrane action and also the critical temperature method. I'm going to give you an overview of what I'm covering today's video. First at all, we will have a look at some fundamentals of the fire resistance, then move on to the critical temperature method and worked examples, then wrap up with conclusions. Fire resistance is determined by the ability of the construction to achieve adequate insulation, integrity, and load-bearing performance. These three requirements are to prevent the three modes of fire spread from one compartment to another compartment. The insulation requirement is concerned with prevention of excessive temperature on the unexposed surface of the construction to cause further ignition. This is quantified by limiting the temperature increase on the unexposed surface to be no more than 140 Celsius on average and 180 Celsius at the maximum. Integrity failure occurs when fire burns through the construction. Load-bearing capacity is necessary to ensure that the structure does not fail, leading to fire spread from one compartment to another. In the mid-1990s, a series of large-scale structural fire experiments were carried out in an 8-story composite structure at Cardington in Bedfordshire in the UK, in the so-called compartment fire tests. The internal secondary beams were not fire protected. These beams experienced very high temperatures and distorted badly, therefore clearly contributing very little to fire resistance of the structure. The load-carrying mechanism that enabled this performance was identified as tensile membrane action (TMA) in the composite slab at very large deflections. TMA can be used to safely eliminate fire protection to interior secondary beams, as illustrated in this figure. At ambient temperature, composite slabs are considered as one-way spanning between secondary beams. However, in the fire situation, if there is no fire protection to the interior secondary beam, the composite slab becomes two-way spanning and is supported by the edge beams. At small deflections, bending behavior governs, and the load-carrying capacity of two-way spanning slabs is quantified based on yield line theory. However, at very large slab deflections that can be generated in fire, tensile membrane action can develop, which can provide the composite slab with load-carrying capacities many times the yield line capacity. It is this increased load-carrying capacity in tensile membrane action that enables the composite floor slab to achieve sufficient resistance without the interior secondary beams. Tensile membrane action, as the name suggests, is mobilized when the tensile reinforcement mesh of the composite slab acts as a tensile net. The in-plane tensile force of the tensile net is balanced by the compressive force that can develop in a concrete ring around the edges of the slab, as illustrated in this figure. Therefore, there is no requirement for external horizontal in-plane restraint to anchor the tensile force in the reinforcement mesh. Structural fire resistance assessment can be carried out either in the temperature domain to find out the critical or limiting temperature given the design load, or in the load domain to calculate the structural load-carrying capacity, knowing the structural temperatures. These two methods should give very similar results, but there are some differences due to different assumptions. In this video, we will present critical temperature method and the temperature of protected steel. First, we will introduce the critical temperature method. Although it is given to calculating the load-carrying capacity of a composite beam at elevated temperature load domain, the target of fire resistance design is often to find the critical temperature that can be survived by beam at a given loading condition, temperature domain. The loading condition will have been determined from ambient temperature considerations, but the structural temperatures are unknown due to unknown fire protection. The load-bearing capacity calculation method can be used to find the critical temperature, but an iterative process is necessary to find the critical temperature without iteration. The critical temperature method may be used. The critical temperature is the maximum temperature in the critical element of the member that can be survived by the structure without losing load-bearing capacity. For composite beams, the critical element is the lower flange of the steel section. The critical temperature is a function of the level of applied load of the structural member. To calculate the load level, we have this equation. Since bending moment resistance usually governs fire design, the design effect of actions for fire design, EFIDT, is the maximum bending moment in the beam for the design, and RD is the composite beam bending resistance for ambient temperature design. To calculate the maximum yield stress ratio of steel, the load level is then converted to the minimum value to which the elevated temperature yield stress of steel can be reduced. For fire resistance rating greater than 30 minutes, we have this equation. For 30 minutes fire resistance rating, R30, we have this equation. To find the critical temperature, using this steel yield reduction factor, the critical temperature can be found based on the yield stress reduction factor temperature relationship in this figure. The 0.9 multiplier in the previous equation gives a yield stress ratio for R30 lower than that for higher fire resistance ratings. Therefore, at the same eta FIT, the critical temperature for R30 is higher than that for higher fire resistance ratings. This slight increase in critical temperature, compared with that for higher fire ratings at the same load level, is to take advantage of non-uniform temperature distribution in the steel section. In fire, the temperature of the steel top flange at first rises more slowly than that of the bottom flange, because the top flange is in contact with the cooler concrete slab. The critical temperature method assumes that the temperature distribution on the steel section is everywhere that of the exposed bottom flange. A valid assumption for long fire resistance periods, when a longer heat conduction time allows the upper flange temperature to reach almost the same temperature as elsewhere. It is conservative for 30 minutes fire resistance, because the upper flange maintains a much lower temperature than elsewhere due to a shorter heat conduction time. The use of a higher critical temperature compensates for this. Now we will use an example to illustrate the critical temperature method. The standard fire resistance rating is 60 minutes, R60. For complete shear interaction, the full interaction bending resistance at ambient temperature is MPLRD equal to 829 kN. The maximum bending moment for fire design is 258.5 kN. From this equation, we obtain eta FIT equal to 0.312. The steel yield strength is reduced to 0.47 and 0.23 of the ambient temperature value at 600 Celsius and 700 Celsius respectively. Linear interpolation gives a critical temperature of 666 Celsius. For comparison, if the fire resistance rating were R30, and the beneficial effect of non-uniform temperature distribution in the steel section were taken into account, then we obtain this factor, for which the critical temperature would be 679 Celsius. For partial shear interaction, the degree of shear connection is 0.46, and the bending moment resistance is 693 kN, so the load ratio is 0.373. Interpolation using the results gives the critical temperature as 640 Celsius. When exposed to fire from beneath, the shear studs are shielded by the concrete slab. Their temperature is much lower than the steel section temperature, Therefore, shear studs suffer much lower reduction in strength compared with the steel section. This means that their degree of shear conduction tends to increase in fire compared with that at ambient temperature. Therefore, the critical temperature for partial shear interaction tends to be higher than that for complete shear interaction, if the load ratio is the same. Now we will introduce how to calculate the temperature of protected steel. To limit the temperature rise of the steel section to the critical temperature, fire protection is usually required. The required fire protection thickness depends on the fire protection method, as well as the fire protection material. Usually, specific fire protection material manufacturers should be consulted. If reliable thermal properties of fire protection materials are available, the temperature calculation equation may be used to find the required fire protection thickness, as shown here, where lambda P is the thermal conductivity of fire protection material, Dp is the thickness of fire protection material, API is the area of the inner surface of the fire protection material per unit length of part I of the protected steel member. Vi is the volume of part I of the steel member enclosed by fire protection material. Ca rho A are the temperature-dependent specific heat and density of steel. Cp rho P are the temperature-dependent specific heat and density of fire protection material. Theta Fit is the fire temperature at time t. Delta theta Fit is the increase of fire gas temperature during the time interval delta t. For standard fire resistance design, the fire temperature time relationship is this equation, in which T is time and theta infinity is the temperature of ambient air. This figure shows the cross-section profile of steel section with a concrete slab on top. If box protection is used, the entire steel member is assumed to have the same section factor. It is the ratio of the inner surface area of the box protection per unit length to the cross-sectional area AA of the steel member per unit length, as shown here. If profiled fire protection is used, the current Eurocode allows the steel section to be divided into the top flange, the web, and the lower flange, and their temperatures to be calculated individually. Now we will use an example to show the calculation of the temperature of protected steel. Box fire protection using vermiculite is assumed. We want to know what is the required fire thickness, so that the maximum temperature in the steel section is 666 Celsius, as calculated in the previous worked example. For structural steel, we have the properties of density ρA, and for temperatures up to 600 Celsius, specific heat Ca, as this equation, where theta A is the temperature of the steel in Celsius. For the fire protection material, its thermal properties are shown here, where theta P is the fire protection temperature. The section factor for the entire steel section shows here. The required fire protection thickness for complete shear interaction is 12.5 mm, and that for partial shear interaction is 13.6 mm. This figure shows the steel temperature time relationships, calculated using delta theta AT equation. The steel temperatures at 60 minutes are 665 Celsius and 640 Celsius respectively, not exceeding the critical temperatures of 666 Celsius and 640 Celsius for complete and partial shear interaction. From conclusions, what we learned: steel loses strength when heated sufficiently. The critical temperature of a steel member is the temperature at which it cannot safely support its load. Concrete structures often meet code require fire resistance ratings, as the concrete thickness of the steel rebar provides sufficient fire resistance. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative. and that you learn some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.